Hello, welcome back everyone, and welcome to class number 25 of Physics 218. We're going to begin discussing chapter 3 of Townsend today. Let's just remind ourselves about what we did last time. So we discussed how to calculate the expectation value of the x component of momentum, p sub x, the expectation of px squared, and the uncertainty in p sub x from the wave function. We also discussed graphs of energy as a function of position for a system, something we'll start to use more beginning today. So our goals for today are as follows, sort of to give you the big picture. We're going to talk about how the time-dependent Schrodinger equation, which is what we've been looking at so far, can be simplified to only have spatial dependence. That's the time-independent Schrodinger equation. We'll then talk about solving the time-independent Schrodinger equation for our first non-zero potential energy, namely the infinite square well, or sometimes called the particle in a box. So we'll see how this particle in a box only permits discrete energies for the system. This is what we call quantum behavior, where something is quantized or only comes in discrete levels. So we'll see how the allowed energies are discrete, and we'll take a look at the wave functions corresponding to those energies. But before we dive into this, though, what I'd like us to do is to just refresh our memory of energy graphs. I want to go to a slide on my computer, and then I'll ask you to think about a clicker question. So let's take a minute to remind ourselves about energy graphs, as we talked about in recitation. So again, these are graphs of the energy of a system. So here we're looking at potential energy in blue as a function of position. The total energy is constant, right, because the system is assumed to be isolated. And then the kinetic energy is the difference between the between the total energy and the potential energy. The particle classically can't go to where the kinetic energy would end up being negative. So while we didn't call it that yesterday, such regions are known as classically forbidden regions. So let's take a moment now to do a clicker question about a potential energy diagram. So here we've got potential energy as a function of position. So take a moment and let's think about this. Okay, so if you've had the chance to think about this, you've probably found that the correct answer is D. So if the particle has 5 joules of energy, right, the total energy is going to be right here, right? And so, right, its kinetic energy will go to 0 at x equals 2 millimeters and x equals 8 millimeters, kind of like a mass on a spring. The particle will undergo oscillations between those two locations. Great. So, what I've written for you here is the full time-dependent Schrodinger equation that we've been thinking about so far, right? It talks about both the spatial and the time variation of the full time-dependent wave function, capital psi of x and t. So there's an important case that I want us to look at now, which is, so if our potential energy is constant in time, so there's no time dependence in the potential energy. This simplifies using what's called separation of variables. Now, I have a couple of remarks here. So the potential energy being constant in time, that's actually a really common and situation, one that you have already encountered many times in your physics career. So maybe the best example you might think of is consider, let's say, like a ball that's interacting gravitationally with the Earth, right? So the Earth's gravity is basically constant in time, right? So that's a potential energy that's not time dependent. Similarly, if I have a mass on a spring, assuming the spring doesn't rust over many years or something, right? We can think of that as having a time independent potential energy. There is one sort of important case that you cannot handle with this formalism, namely the interaction between atoms and light. Because if you think of, however you want to think of light, right? If you want to think of light as a classical wave, even though we know that's not the complete picture, right? Anything that's a wave-like quantity depends on both position and time. So if my fist is an atom and there's light shining in at me, the interaction between the atom and the electric field associated with the light wave is going to depend on time. So what we're going to talk about, you can't handle with that situation with this technique. To learn how to deal with time-dependent problems, you're probably going to either have to convince somebody in the department to teach a Physics 470 special topics on super advanced quantum mechanics beyond even the level of Physics 421, or more likely you'll have to go to graduate school. Aside from light interacting with atoms, this is actually not a big. This is actually not a big deal. Now, the other thing I wanted to say is that the details of separation of variables are a little bit involved. I'm going to make a bonus video for this class where I work through that. Separation of variables is, without a doubt, the physicist's sort of first thing in your toolbox for solving partial differential equations. That said, I will not expect you to be able to do that for yourself. This is a somewhat mathematically advanced topic. Whether you do much with it is, I think, going to depend on the instructor in courses like Advanced E&M and Advanced Quantum. So it's definitely, the details are beyond the scope of 218. That said, it is such a widely used mathematical technique, and frankly mathematical and physics technique, that it's really worth seeing this at some point in your life. Certainly, if you're interested in doing research with me about how light scatters, well, all of that boils down to understanding, a lot of that, understanding the details requires you to understand this well. It's not just relevant in physics. The same technique can also be applied to the partial differential equations that govern things like fluid dynamics and heat flow. So if you're thinking about pursuing graduate work in an engineering discipline, this is still worth knowing. Okay, so I'll stop talking about that, but we'll skip ahead now to sort of the takeaway. So it turns out, by separation of variables, that we can construct solutions to the time-dependent Schrodinger equation. So I'll abbreviate that as TDSE. of the form psi of x t. So it turns out to be a product of something that has spatial dependence and then a known time dependence. So psi of x, e to the minus I times e t over h bar, where the spatial part wave function, so that's lowercase psi of x, satisfies the what we call the time independent Schrodinger equation. And what the time independent Schrodinger equation looks like is minus h bar squared over 2m d squared psi. This is now an ordinary differential equation because lowercase psi only depends on position, dx squared plus v of x lowercase psi of x equals e psi of x, where and E is a constant, but it turns out to be something really important physically. It's the energy associated with this particular wave function. Associated so it's the energy of the system, so the particle and whatever it's interacting with. Okay, so just a couple of quick remarks here. So I'll go through the proof of this in the bonus video. We can already kind of see why this is called separation of variables. We've separated this full time dependent psi into the product of two things. One thing, our spatial wave function lowercase psi only depends on position, and then this complex exponential part only depends on time. There's no position dependence here. So we sort of have separation in the sense that we have something that's only a function of x multiplying something that's only a function of time. Why this is better, in some sense, is that this now, the time-independent Schrodinger equation, is now just an ordinary differential equation, no longer a partial diff eq. And that's a big step in making this easier to solve, as we'll see. Moreover, the time dependence is now known and takes a relatively simple oscillating complex exponential form. Okay, so let's see. So what we'll do next is we will think about how to solve the time-independent Schrodinger equation for a particle in a box, because once we've done that, we'll know how to construct the full time-dependent wave function. Before we dive into the infinite square well, I forgot that there were two more things I wanted to mention about the time-independent Schrodinger equation. So it turns out that solves of the TISE are what we call stationary states. And they're called stationary because the probability density associated with the full wave function turns out to be constant in time. Let's see, squared is constant. So let me show you how that works, right? So we said that solutions to the full Schrodinger equation we can construct, right, by taking psi of xt and multiply it. So we take the solution lowercase psi and multiply it by this complex time factor. So e to the minus I e t over h bar. Well, that means our probability density just comes from taking this and multiplying by its complex conjugate. So psi of x t squared. So it's going to be the wave function times its complex conjugate. So if I complex conjugate the entire thing, I'm going to have psi star of x, because in general the spatial part of the wave function can still be complex. And then the phase factor is going to go to e to the I et over h bar. And so notice now that when I have these two phase factors, right, we have e to the minus I something, e to the plus I something, that cancels to 1, so this ends up being psi lowercase I of x, lowercase psi star of x, right? And now, because by construction, lowercase psi doesn't depend on time, this probability density does not depend on time either. So that is shown. The other remark I wanted to make is that you can combine different solutions of the time-independent Schrodinger equation and still build up solutions of the full time-dependent Schrodinger equation. So we'll look more at that on Monday when we start to look at more complicated time dependence. So can combine stationary states and still solve the Schrodinger equation. So namely, for example, so rather than write the most general thing, I'll just write i.e. You can just have a full time dependent wave function that goes like psi sub 1 x e to the minus I e 1t over h bar plus psi 2 of x e to the minus I e 2t over h bar, so long as psi sub 1 satisfies the time-independent Schrodinger equation with energy E1, and psi 2 satisfies the time-independent Schrodinger equation with energy E2. So we'll talk about this combination idea in much more detail next week, because it's really, really cool. Okay, so now I'll erase the board and we'll start thinking about the infinite square well. So, as we prepare to think about the infinite square well, let me first tell you about a general procedure for solving the time-independent Schrodinger equation. We'll apply this procedure to the infinite square well, and then in chapter 4 to several other physically relevant potential energies. So the first step is always going to be to write a general form of the solution to the Schrodinger time-independent Schrodinger equation given some potential energy V of x. This might need to be done piecewise if the potential energy is defined in some sort of piecewise way, as we'll see for the infinite square well. The next step will almost always be to apply some boundary conditions. Again, I'll say more about this shortly, but what that says is that there's usually some constraint on the behavior of the wave function either at any discontinuities in the potential energy or at x approaches plus or minus infinity. Usually these boundary conditions will allow you to determine what energies E are allowed that satisfy the time-independent Schrodinger equation, and then once you do that, you'll be able to determine and normalize what the allowed wave functions psi of x are. So now let's turn to the infinite square well. We'll talk about what that potential energy looks like, what it can physically represent, and then we'll start applying this procedure. So, as you saw in the reading, the infinite square well potential energy looks like this. So the potential energy is defined in the following way. It's equal to 0 for x between 0 and L. And then otherwise, the potential energy is infinite. So let's talk a little bit about the physical significance. Right? So in here, in this region, 0 to L, where V is 0, so particle is non-interacting in this region, but out here we have an infinitely high potential energy. Particle can't get here, so or over there. So you should think of this in some sense as a particle that's free to move between 0 and L, but is confined by essentially infinitely hard walls, you can maybe think about it, at 0 and L. Now this looks like a rather artificial potential energy, and in fact it is a little artificial, but it's not completely devoid of physical context. So we're looking at a one-dimensional version of this for mathematical simplicity, but there are some real-world applications of this potential energy. So, applications. So it does turn out to be relevant, at least a three-dimensional version of this, or two or three-dimensional version, of something called a quantum dot, where you have some small chunk of material where you maybe have electrons that are basically non-interacting inside the material, but they can't get out of that material, so they're confined like the 1D version we're talking about, quantum dots. The other place that this is relevant, it turns out to be applicable to understanding the physics of metals. So if you want to understand how metals, say, conduct electricity, again, to sort of really good approximation, it turns out that the electrons in metals are basically non-interacting inside the metal. They're basically free to move, but they can't get out. So this infinite square well model in its 3D version can be relevant. So you might talk more about that if you take thermal physics, or if you go and take a solid state physics course at some point. Okay. Having talked about what the infinite square well looks like, let's start to think about how to carry out that four-step procedure I talked about. So, as I mentioned, the first step is always to try to write down the general form of the solution to our time-independent Schrodinger equation. So let's first think about what happens, and we've got sort of three chunks to deal with. We want to think about x less than 0 when v is infinite, we want to think about the part of the well in the middle, and then we want to think about the part for x greater than L, where again the potential energy is infinite. Oh, let me just sketch that up really quick. So L V, just so that we remember, something like that. Okay, so we'll deal with, it turns out, all the parts where, so A, where the x is infinite. Okay, well, think about that, right? If I plug in infinity over here, that's going to give us something really, really weird, right? This sum of terms is looking like it have to be infinite, which kind of suggests that either you need an infinite energy, which doesn't make sense, or you need an infinite wave function. But an infinite wave function doesn't make sense either, because we know that the wave function has to be normalizable. Infinity is so sort of weird that the only way out of this, the only way to get a physically reasonable solution, the only plausible thing is for the wave function to vanish where the potential energy is infinite. And this sort of corresponds, at least somewhat, with our physical intuition, right? We said that with an infinitely high potential energy, and based on what you know about like turning points and stuff, nothing, right, will ever have enough energy to like get past zero and get to the left of zero or to the right of L. And so it maybe shouldn't surprise you that there'll end up being zero probability of detecting the particle outside my box. So hopefully this is at least, this seems both physically plausible and mathematically reasonable. So the more interesting part is where v of x equals 0, so that's here between 0 and L. Okay. If v is 0, the TISE becomes, right, equals E psi. Now we can simplify this a little bit. I'm just going to shove all of the constants over here to the right hand side. So I'm going to multiply by minus 2m and divide by h bar squared. And that gives me d squared psi dx squared equals minus 2 times m times e over h bar squared psi of x, where this is all a bunch of constants. Now, it is typical for us in physics to sometimes lump constants together and define new constants. It certainly is a helpful trick if you're doing algebra, so I'm going to do that. For reasons that will be clear, I'm going to define this lump of constants k squared as k squared, so I'll call that k squared is defined as 2m e over h bar squared. We'll see that there's a reason for that choice in a little bit. But now I've got a whiteboard question for you. So can you think about how this equation, this ODE, could be solved for psi of x? I think you might already know the answer to this based on having seen some similar things in 217 and 225.